Okay, we'll get started here. Once again, thank you for joining us for this session of Applied Day. Before we dive in, I just want to give a quick background of applied engineering. For over 35 years, Applied has been helping companies overcome their engineering challenges, whether that be with our technology team providing training, implementation, or support for software and hardware solutions, or our services team providing design and manufacturing engineering, as well as software development and reprographics. We fit your needs and your business. With that, I will turn things over to our presenter, Alex Sinclair.
Good morning, everyone, and thank you for attending this Applied Day webinar titled Applied Advanced Engineering and Analysis. My name is Alex Sinclair, and I'm a simulation and mechanical design engineer here with Applied. The topics we're going to cover today, we'll kind of start out with the generic advantage that we believe simulation and analysis can provide. The real bulk of this presentation will focus on finite element analysis types and capabilities. We'll kind of divide those into two categories, static and then transient and dynamic. We'll also talk a little bit about computational fluid dynamics, coupled systems and multiphysics, and ANSYS's partnership with ESSS Rocky. So with that being said, we'll dive right in. Starting kind of with the simulation advantage and the value proposition, we really believe simulation analysis is most advantageous when plugged into the design cycle. And so here we can see our traditional design cycle of our detailed design followed by building our prototypes and testing those prototypes. If we can plug in analysis and kind of shortcut this loop where we can iterate on our designs and virtually test, we can save a significant amount of time and financial resources, by shortcutting the design cycle. So again, we really feel that this is the primary value proposition with analysis, but there are some other useful bits with simulation in general. Some of those things are listed here. Insight into structural behavior otherwise unavailable without extensive testing. We can detect premature failure. Again, we can reduce design cycle times. We can reduce prototype costs. We can decrease defect rates and product warranty costs. We can also remove excess costs from overdesign, improve product performance, and optimize products, all with various simulation tools. We do, here at Applied, our team feels pretty strongly that a fundamental understanding of finite element method and the finite volume method for CFD and some experience is strongly recommended. There are many challenges with setting up some of these simulations and analyses. Things like complex contacts, lots of degrees of freedom, how much simplification do we need? What are our boundary conditions going to do to affect the stiffness of the model? And what are all those things going to kind of contribute to our overall computational expense? And it can be fairly easy to make mistakes or misinterpret results. So again, some experience is definitely helpful when looking to set up some of these simulations. Next, we'll move right into our static analysis. And so here we're going to cover three topics. We're going to cover our static structural analysis, which is kind of like the jack of all trades, the load deformation analysis that we're typically going to be performing. We'll also look at buckling analysis and steady state thermal analysis. Okay. Starting with static structural analysis, this type of analysis determines the displacements, stresses, strains, and forces in a structure. Static structural analysis is a time-independent or quasi-static analysis, and this means that the load is assumed to be applied slow enough that we're basically neglecting acceleration. Okay, and I have the structural inertia equation listed here. And for static structural analysis, we actually simplify that down to the linear matrix and nonlinear matrix form. And so it's again, no dynamics at play here. We do have a wide range of applications with static structural analysis. Again, it's kind of like, it's the typical analysis that we're going to be performing on a day-to-day basis. We can look at complex structures, weldments, assemblies, machinery, frames, chassis, and structures, structural components, testing equipment, even things like consumer products and biomechanics. And we have a wide range of materials and a pretty vast materials library that we have available to us for looking at a lot of these different products and designs. We do have a couple of examples of previous projects the Applied team has worked on. The first is a Doosan Bobcat compact track loader, and this is a bucket prying load case. We can see kind of the complexity that goes into this kind of analysis. We've got several, sub-assemblies and weldments, the carriage, the frame, the lift arm, the bucket that kind of all come together to form this machine. We even have hydraulics, so we've got lots of degrees of freedom here. So again, we have a fairly complicated analysis, and similarly, the same is true for this Doosan Bobcat excavator. This is an upper structure and work group with a digging load case, and so we can see, all the pivot points that go into this. We've got our hydraulics. And so again, we can take into account very complex structures with static structural analysis. We also have a cantilevered hydraulic boat lift. This is a ShoreMaster product, and this example is an 8,000 pound lift throughout its entire range of motion. And so I'll play, this is actually a video, and I'll play this video. Now I mentioned that static structural analysis is, it's quasi-static, so we're not taking into account time, but here it seems like we're kind of, we're running this through the range of motion. So, you might think that we are including some time here, but actually what we're doing here is we just have this setup run at multiple different positions, and we kind of combine those all together to create this video. So we're actually still not including time in this analysis. I'll play the video one more time so we can kind of see the load, kind of sink the top bunk down, and then the hydraulics actuate and lift the lift up. Moving on, we'll talk about buckling a little bit. Buckling determines the critical buckling forces for a structure. We have two types of buckling analysis. We have linear buckling and we have nonlinear buckling. So we'll start with linear buckling, or eigenvalue buckling. This is an eigenvalue problem, which is kind of a textbook approach. If we think back to our university days, we studied linear buckling. Linear buckling is the initial step in determining if a component or structure is at risk of buckling. So if we are at all concerned of a structure or component to be at risk of buckling, this is kind of where we'd start. Linear buckling is typically non-conservative, so it is, again, it's kind of the first step, and we'll go through that after we kind of look at nonlinear buckling. Nonlinear buckling is a more realistic analysis that we actually perform in the static structural environment, which is the previous environment that we discussed. In the static structural environment, we can capture all the nonlinearities, all the complex contact. A lot of times buckling analysis is not stable, and so it can be a little bit more challenging. But another advantage of nonlinear buckling is that we can, if we can get all the buckling to solve, we can actually look at the post-buckling shapes and load carrying capacities of a post-buckled member. And so a lot of advantages to nonlinear buckling, although it is significantly more computationally expensive. If we look at the graph on the right, this is a bifurcation curve that kind of displays the difference between eigenvalue buckling and nonlinear buckling. The blue dot would be the critical buckling load that we would predict during linear buckling, and the red dot would be the critical buckling load that we would predict during nonlinear buckling. So we can see the nonlinear buckling is certainly predicting a lower load, and so our linear buckling is typically non-conservative, but it is still a great starting point. We do have some examples of buckling. This particular analysis we're going to look at here was run in the linear buckling environment. This is a channel under a compressive load. It's fixed at the bottom, and we have a unit load applied to the top. And so here we're going to calculate our load multiplier and our buckling shape. Okay, so that's the graph on the right. We can see our load multiplier here of 10,430 pounds, and we have our buckling shape. We can see the flanges of that channel are flaring out a little bit, with a little bit of the web kind of pushing in towards the edges of those flanges. Okay, and so again, we're predicting 10,430 pounds with the linear buckling. Very easy analysis to kind of set up and just get a ballpark number for. When we move into nonlinear buckling, where we're taking into account all the nonlinearities of the material and deformation, we're going to generate this force versus displacement curve, and we can see that this is not linear. Okay, and this force versus displacement curve is leveling off at about 9,500 pounds. And so if we compare that to the linear buckling, we're about 9% over predicting the buckling load, critical load multiplier by about 9% with the linear buckling. So we're over predicting with linear buckling. We can see our buckling shape here with the nonlinear buckling is exactly what we predicted with the linear buckling, but our load is somewhat lower, and so we do over predict with the linear buckling again. Moving on, we'll briefly talk about steady state thermal here. Steady state thermal analysis determines the temperatures, thermal gradients, heat flow rates, and heat fluxes in solids due to steady state thermal loads. Similar to buckling analysis, this is kind of the first step in this process, or the first step in thermal problems. I do have the governing equations for heat conduction listed here, kind of simplified into their matrix and linear matrix form at the bottom there. So similar kind of set of equations to our previous slides. We did put together a brief example just for this webinar. This is a steady state thermal example of a coffee mug on a warmer. So we have a thermally insulated warmer with an internal heat source. We've got a coffee cup with coffee at 72 degrees and external air at 72 degrees, okay? And so this type of problem, we're only looking at the conduction equations, okay? So we're not actually using real fluids, we're using convection coefficients here to kind of simulate the heat transfer through the boundaries. So we'll look at, we ran this with a couple of different cups. We ran with a ceramic cup and a metal cup. Ceramic cup being, this is going to be a little more thermally insulative than the metal cup, and so we can kind of see the heat flow as it approaches, as it calculates the end time or steady state conditions there. And if we compare those to the metal cup, we can see that the metal cup is a little bit more conductive. We're even getting some of that heat into our handle, which could potentially be an issue if our handle gets too hot to be able to pick up our coffee mug. This is something that you might even have on your work desk to keep your coffee warm. So just kind of a quick, interesting little project to kind of demonstrate the steady state thermal analysis capabilities. We'll move on now to the transient dynamic portion of the analysis. This has several more topics that we will cover. These topics include modal analysis, harmonic response analysis, random vibration analysis, response spectrum analysis, rigid body dynamics, transient structural analysis, explicit dynamics, and transient thermal analysis. So we'll dive right in. We'll start off with modal analysis. Modal analysis determines the vibration characteristics of a structure or component, okay? And these characteristics or properties are going to be intrinsic to the structure. So it's going to be based on the stiffness, the boundary conditions, and if we have some loading that influences the stiffness of our model, that's those properties are going to be intrinsic. So a mode, we define a mode as a deformed shape, and those mode shapes correspond with a natural frequency. Again, like similar to buckling, this is an eigenvalue problem. We don't require damping for modal analysis, although we can use it. And really, this is typically a precursor or even a complementary analysis in many cases. And so as we go on here, we'll see some of those, analyses that are kind of based on modal analysis as we kind of move along the vibration analysis types as we go through the presentation. Applications for modal analysis, really, any structure or component that's subject to vibration or even force vibration. We do have an example, kind of a classical modal analysis example of a cantilevered beam. This beam is fixed at one end. There's no load applied to this beam. And so we calculated mode 1 and mode 2 for this cantilevered beam. I've got the two mode shapes here. Mode 1 occurs at 6.2 hertz. It's kind of just a simple bending mode. Mode 2 occurs at 39 hertz. It's a little more complex bending mode. It's got an inflection point about 3/4 of the way through the beam. And I'd like to make note of that. We're going to come back to mode 2 here in a little bit after we have a chance to look at some harmonic response analysis that's been performed on this same beam. Okay, so here's our two modes and our modal frequencies for this classic cantilevered beam example. Moving on to harmonic response analysis. Harmonic response analysis determines the steady state response to sinusoidally varying loads and excitation. So here we're actually applying a load or a forced vibration, okay? Whereas modal analysis, we're just calculating an intrinsic property of the structure. In harmonic response analysis, we're actually applying a forced vibration. We can use this environment to evaluate the harmful effects of forced vibrations, things like resonance, or look at fatigue life, things like that. without using the full transient setup, okay? And really, this is a simplified transient analysis, and we simplify it by assuming that the response occurs at the same frequency as the loading, and this would be steady state. So our response is going to be steady state with our loading. So if that assumption is true, this analysis can be, a great tool, a very computationally efficient tool, provides significant reduction in computational time and data generation compared to full transient analysis. And again, this is an extension of modal analysis. We will use modal superposition to perform this analysis. We can use a range of input load frequencies. So say we could have a 50-pound load and we could run it from 0 hertz to 100 hertz. And so we can get that steady state response, at all those different frequencies. Or we can just, focus on one frequency. We do output stress and strain data from this, so we can use it as a life prediction. We do have an example of a harmonic response, same example as before. We've got that cantilevered beam fixed at the one end with the load applied to the other. Here we're going to apply a forced vibration to this cantilevered beam at the end of the beam tip. This load's 50-pound force, and we're applying it at 39 hertz. So I'm just focusing on a single frequency here just for simplicity. Again, 50-pound load, sinusoidal load, 39 hertz. Okay, and so next we're going to get the output from the harmonic response beam tip deflection. Okay, and this is again at 39 hertz. So the output is steady state, so it's occurring at the same frequency as our input load. 50 pounds, we can see that the deformation is, plus or minus around 0.33 inches. Okay, so this is our steady state response. And I did run this in full transient just to kind of get kind of a comparison here. So we can see the same beam with the same load runs in the transient environment. So we can see that, the first 2 seconds, we really haven't achieved steady state yet, but at 2 seconds, we are approaching steady state conditions. Here we go. And so if we were to keep running the transient analysis, we would converge on the result we get in the harmonic response environment of the plus or minus 0.33 inches. Okay, I hope that makes sense to everyone. We're going to move on to the stress strain output from the harmonic response. And so here is again the stress strain output from that harmonic response load. So here's a steady state response of that beam under that load. This is kind of a combination of mode 1 and mode 2 that we're seeing here. But we are getting, some significant influence from mode 2. You can kind of see that inflection point 3/4 of the way down the beam. And what's interesting about this is for a classical beam example that's fixed at one end and we apply a load to it, we would expect the maximum stress to be at the fixed end, right? But here, when we're working with forced vibrations, we're actually seeing the max stress occur at about 3/4 of the way down the beam where that inflection point is at. So that might not necessarily be intuitive to us, when we start looking at problems like this. And so I have the mode 2 shape here just for comparison, so we can kind of see that inflection point that occurs, at that location where we're seeing that high stress. So very interesting result here. Definitely important to note. Moving on to a modal analysis example. This is a Superior brand incline aggregate material classifier. This machine has got two motors that excite this screen, and then we would run aggregate material across this to separate this into different constituent sizes. And so being a piece of vibrational equipment, we want to make sure that we're not running this machine near any of its resonant frequencies, and so we can predict those with modal analysis. This was actually a modal analysis done with a pre-stress calculation before that, so fairly complicated type of analysis. We also have a DPF DOC from Doosan Bobcat that our team ran here, and this is another modal analysis with a pre-stress calculation. This is basically an engine after treatment product. This bolts up right to the engine and processes the exhaust. In engines, they tend to vibrate a little bit, so we want to ensure anything in close proximity to the engine is not going to resonate or damage itself due to those forced vibrations. So another great example here from one of the projects we did with Doosan Bobcat. Next, we'll briefly talk about random vibration analysis. This type of analysis determines the response of a structure due to vibrational loads that are random in nature. Okay, so random in nature, that means they're non-deterministic vibrational loading. So kind of an example of this would, if we attached an accelerometer to a truck and drove it around, every time we drove it around and ran that test, we would get a different set of accelerometer data. We'd never get the same exact set. So it's non-deterministic in nature. This excitation, when we do this type of analysis, is applied using power spectral density functions, and it's applied as a basic excitation. Generating these PSDs is, uses a statistical method, and so we have a statistical output in the analysis as well. We can use multiple PSDs, and again, this is an extension of modal analysis, and we use modal superposition to do this analysis. PSDs, I think, if anybody in the audience has any experience with shaker table testing, you'll be very, very familiar with PSDs. That's how we drive our shaker tables. Some applications of random vibration analysis. This is a like I previously mentioned, widely used testing methodology to simulate real-world vibration. So again, an example, automobile component, engine noise, road noise, acoustic noise. And we use this a lot in shaker table testing. We do have an example of a PSD generation. I'm not going to get into the specifics of how we do this. The algorithms are somewhat complex, and we do typically use software. But here is an example of a time history of some truck bed accelerometer data. Okay, and so attach accelerometer to a truck bed, drive it around. This is kind of over the 6,700 seconds, this is what the accelerometer measured. Okay, and so we'll actually, to generate a PSD, we'll use software to convert that time domain of acceleration into power versus frequency. Okay, and so we'll take a look at how much power is present at each frequency, and this is actually what we'll use to drive the random vibration analysis. So here's our random vibration analysis on that same beam. We used a 3 sigma scale factor, and so we're 99.73% confidence interval, and our max stress is 902.33. So we have a statistical output in the stress contour here. And so we'll move on to the response spectrum analysis. This type of analysis determines the maximum response of a structure for given input excitations. This is deterministic vibrational loading, where the maximum response is calculated from the input response spectrum. We have several methods to combine, these input responses. This is widely used in civil structure design. We don't have an example for response spectrum, so we'll move right into rigid body dynamic analysis. This one, kind of a cool type of dynamic analysis where we're looking more at kinematics. Rigid body dynamic analysis determines the dynamic response of an assemblage of rigid bodies. And we can assemble these rigid bodies or link them together using different types of joints, different contacts, springs, dampers, etc. So think back to our dynamics and our vibration, our suspensions, things like that. We can use this solver in this environment to rapidly study kinematics. So it can be a very useful tool. We're going to output forces, moments, displaces, velocities, and accelerations from this analysis. We are not outputting stress and strain results. So we're not using this to predict life or predict failure or anything like that. We're just studying kinematics. We can, however, use those outputs to run a subsequent stress strain analysis in the static structural environment. So those output quantities can be very useful downstream once we kind of get our kinematics to be what we want them to be. Very robust solver in the rigid body dynamics environment, so we get pretty significant efficiency over running a full transient dynamic analysis. First we have some applications, robotics, suspensions, many types of machines with moving components, engines, transmissions, the list could go on and on here. Anything that has some type of kinematic behavior that we want to tune, we can use this to study that. Do have an example of a Formula One front end suspension. We're going to apply a 6G bump to those tires in this example. And so we can see the top right displacement curve. That's actually how this load is applied. We're applying a displacement to the tires over 0.2 seconds of time, which results in our 6G acceleration. And I've also got the velocity and acceleration calculations from that curve there. So let's go ahead and look at the reaction of this front suspension due to that bump. So we can see the bump here, and we can see the reaction of the linkages in the frame with the spring and damper system that we have there. And so it looks to me like this frame or the suspension could use a little work. We're a little saggy in the middle, And again, this analysis runs very fast. It's very easy to set up. Very capable solver here. Moving on to transient dynamic analysis. This type of analysis, transient dynamic analysis, determines the dynamic response of a component, structure, or assembly under a time varying load. So similar capabilities to the static structural environment, we're just adding time back in now, okay? So we can output forces, moments, displacements, stresses, strains, velocities, and accelerations. So kind of the whole shebang, everything. Very computationally expensive here. I've got the structural inertia equation listed again. We're not going to be simplifying it this time like we did for static structural analysis. We have everything, the mass matrix, the damping matrix, the stiffness matrix, and then we've got, time. This is the linear form, but we can also have all the same nonlinear capabilities in this type of analysis that we typically would use in the static structural environment. And so the applications here, I kind of just give a broad comments that, any scenario where you have things that are moving that one of our previous, simplified environments can't take care of properly. So things like drop tests, impact studies, or maybe even modal analysis where we need nonlinear contact. Okay. I do have one example of some transient dynamic analysis that our team has run. This is a high density ball dropped onto a hyperelastic sheet. So we drop that ball and we can see kind of the wave propagation or the response wave through that hyperelastic sheet. So we'll run it one more time here. So it looks like this was run for about 1/10 of a second. Yep, about 1/10 of a second. Moving on. Explicit dynamic analysis. This is very similar to the transient dynamic analysis, kind of with one subtle difference. The explicit dynamic analysis environment, we use this to determine the dynamic response of a structure under a load whose period is significantly shorter than that of the structure. So think shock loading, drop loading, or blast loading, where the time duration of our load is very, very small. That's where we're going to use the explicit dynamic solver. Can be very computationally expensive. We're going to use, it's the LS-DYNA, the ANSYS LS-DYNA solver. We have a lot of capability in this environment that we typically do not have in other environments, things like extensive nonlinear deformation, complete failure of materials. Some of the applications here, think explosive loads, crash testing, or even shock wave propagation through our structure due to maybe some kind of blast loading. I do not have an example of explicit dynamic analysis. We'll jump right into transient thermal analysis. This type of analysis determines temperatures, thermal gradients, heat flow rates, and heat fluxes that vary over time. Go back to our steady state thermal and we'll add time back in. We also add in nonlinearities too. So we can take into account things like temperature dependent properties, temperature dependent coefficients and loads, and even radiative heat transfer, okay? But we have the governing equation for heat conduction written again here, and then we have it simplified down into its nonlinear matrix form. Okay, so this is going to be conduction dominated problems that our steady state thermal couldn't handle. We're not including fluid here, so we can have things like convective coefficients, but we don't have actual convection taking place. Other application examples may be electronics cooling, heat treatments, etc. Now we'll briefly talk about computational fluid dynamics. This is a huge topic. We're kind of going to just scratch the surface here. This is another thing that we do here at Applied Engineering. And computational fluid dynamics, we're using this to determine the flow characteristics, heat and mass transfer phenomena, chemical reactions, etc. We do this using the conservation of mass equations, Newton's second law, conservation of energy equation, and we kind of combine these all together to form our general transport equations, and I have them listed here, solved on a control volume. We won't get too deep into that. We'll kind of focus on some of the basics. We kind of have the same two types of analysis here under the computational fluid dynamic umbrella. We've got the steady state and the transients. Again, the steady state, we're not really predicting how the process achieves the steady state. We're just solving for the steady state conditions. And then the transient analysis, we're solving, as all those conditions change with time, and we're capturing all that data. Applications to this are vast. Things like internal and external fluid flows, aerodynamics, rotating machinery and turbo machinery, HVAC, heat transfer. We can do convection, conduction, radiation, all of it in one. So we can actually have solids and fluids all together here, and we can take care of the convection, the conduction, the conjugate heat transfer, everything. Okay. More examples, maybe electronics cooling. We can even look at reactive flows and combustion in the computational fluid dynamic environment. We typically use fluent here at Applied Engineering. We do have one example of a brief CFDA project I just put together for this webinar. This is a shell and tube heat exchanger. I ran this transient for 10 seconds. And so a brief kind of explanation of what we're doing here. We've got hot water at the inlet there, 90 degrees Celsius. We've got hot water outlet up top, and that kind of comprises the flow through the shell. We also have the tube portion with the cold water inlet at 5 degrees Celsius, the cold water outlet. This heat exchanger is made out of copper, and we have air at 23 degrees Celsius outside the heat exchanger. Here is a picture of the CFD model. We can see our two inlets and our two outlets, and we have our mesh shown here. Next, I've got a temperature contour at the end time of 10 seconds. And so we can see the fluid coming in at 90 degrees Celsius, and we're leaving the temperature outlet or the fluid outlet at the top. We're leaving, at 60, 65 degrees Celsius. So our heat exchanger is certainly cooling the fluid down, which is what it needs to do. Next, we have, I do show the fluid velocity path lines here, so we can kind of see, how the fluid that comes in the hot temperature inlet kind of moves through this heat exchanger. So we can see that there is some turbulence in there and some inefficiency to how those fluid particles move from the inlet to the outlet. So perhaps that's something that could be improved if we were going to look at this further. So that kind of closes up our CFD. Again, CFD is a very vast topic with a lot of capability, kind of just scratching the surface here. We'll briefly talk about coupled systems here. So really what coupled systems allows is the solving of multi-physical problems. And so in a nutshell, what we're doing here is we're combining multiple systems, that we've kind of previously talked about. Perhaps fluid structure interaction would be a good example. Maybe we have a solar panel array that's subject to some type of wind loading, and so we want to actually pass the fluid over the array and generate those wind loads, and then we want to take that a step further and run a stress strain analysis on that structure. And so we can use the coupled systems and the multi-physics solver to do that all at once. Some other examples: conjugate heat transfer. I've got a picture of that here. We've got some electronics with some forced convection through that area there, and so we're cooling those electronics down, and we want to capture that heat transfer and those thermal stresses in the solids all at once. So again, kind of a multi-physics problem there. Another example could be electromagnetic heat dissipation. Lastly, here we're going to talk about a newer product, ANSYS product, partnership with ESS Rocky. ESS Rocky is a 3D discrete element modeling tool which simulates flow behavior of bulk materials, and we can take into account complex particle shapes and sizes. A lot of applications for this, things like conveyors, chutes, mixing screws and devices, material classifiers. We've already looked at one material classifier previously during the modal analysis example, pile dynamics perhaps, and even material crushing. I've got an example. This is an embedded YouTube video of some material crushing here. This is actually a cone crusher. We're dumping rocks in it, and this thing is going to start to break those rocks, and so we can actually predict kind of how that process is going to look like with Rocky here. We've also got another example of a conveyor chute. I'll kind of move this along, but here we can kind of see a conveyor dumping material into a chute, and we can kind of see some inefficiencies in that chute where material is getting stuck in that chute, and so that information can be used to improve the chute so we don't have residual material stuck in this chute. Here's kind of another view of that. So again, bulk materials, flow of bulk materials is what we're looking at with ESS Rocky. And with that, we'll kind of end the presentation this morning. I'd like to thank everyone for attending. I hope it was enjoyable, and we can kind of open it up for questions if there are any here. I will bring up the next slide that has our contact information if anyone has any further questions outside of this webinar.
Yeah, thank you, Alex, and thank you all for attending, and have a great rest of your day.